Hello everyone, welcome to our talk. This is Yulei from University of Technology, Sydney. This is a joint work with Xiao, Guanqing, and Haoyu. This talk will present a new code embedding approach called Flow2Vec, which marries precise static analysis and recent advances in high-order proximity embedding. In particular, we will present how we precisely preserve structural information of code, including interprocedural alias-aware program dependence and context-free language reachability, to better support subsequent code analysis tasks such as code summarization and semantic labeling. Code embedding as an emerging paradigm for source code analysis has attracted much attention recently with the rise of machine learning and natural language processing. As a complement to traditional program analysis, code embedding can conduct a range of tasks that non-learning-based, rigorous static analysis normally hard to perform. For example, automatically generating a semantic label for a code fragment. As we can see here, this code fragment initializes an array of integers through a for loop. It is labeled with initialize to represent the semantic of this piece of code. The basic idea for code embedding is to train a model to learn the label distribution conditioned on the code. This is done by mapping the semantic meaning of a code fragment to a numerical vector representation, or so-called distributed representation, in a geometric space or embedding space, such that the distance between any two node vectors captures the semantic relation between two code fragments. A closer distance between two vectors implies a more similar code semantic. Once the model is trained using existing well-labeled code snippets, it can be used to predict the label of a new code fragment, whose semantic is similar to the existing labeled code fragments in the training set. For example, a new code snippet initializing the array of chars using a while loop is also tagged with the same label initialize. The key of code embedding is to build a compact vector representation that can precisely capture code semantic. The most intuitive way, actually inspired by word embedding in the NLP community, is to treat source code as a bag of textual sentences, so that a code vector can be built by concatenating the vectors of each token in a sentence. Word embedding captures the relationship of a token with its co-occurrence tokens in a sentence. The resulting vectors are close to one another in the embedding space if two code fragments are textually similar. However, source code is not simple text. Two code snippets can be textually different but semantically equivalent, as the two code examples we have seen before. In order to preserve richer code semantic, recent approaches extract structured information based on abstract syntax trees or flow graphs of a program. A typical work is Flow2Vec, which represents code semantic using a bag of passes on the AST of a program. The pass here is an analogy to sentence in the word embedding. In such a way, it can capture the relationship between two tokens in a structured manner. The more sound and precise structural information are preserved, the more effective the code vector can be. However, there are still three limitations of the existing structured code embedding, which may preserve spurious program dependence or miss important relations between tokens in the embedding space. Typical graph embedding techniques work on an undirected graph. Applying these techniques may fail to capture long-range asymmetric transitivity on a directed graph, such as program dependence graph. For example, here is a transitive relation from A to C on the program dependence graph. When mapping the graph space to a low-dimensional embedding space, the approach, which does not consider asymmetric transitivity, measures the bidirectional relation between A and C using the inner product of their corresponding vectors, such imprecisely preserving two reachability relations from A to C and from C to A, though the later one is spurious. Similarly, the existing approaches also fail to preserve and embed imprecisely the structural information such as pointer aliases and interprocedural context sensitivity. For example, without preserving aliases we may obtain incomplete reachability relations in the embedding space. Without considering calls and returns, the result embedding may contain spurious dependence relations. The goal of this work is to push the boundary of existing code embedding techniques to achieve more precise results with less learning efforts by extracting and embedding deep structure information of code. This figure shows the workflow of Flow2Vec, which accepts the LLVM intermediate representation as an input to build interprocedural value flow graph, or so-called IVFG of a program. The IVFG is transformed into an adjacency matrix A. We then formulate value flow reachability as matrix multiplication to embed context-sensitive value flows through CFL reachability in the low-dimensional space. The resulting matrices are used to approximate a high-order approximate matrix M, which is then decomposed into source and target embedding vectors for each node on the IVFG, in order to preserve asymmetric transitivity of interprocedural value flows. Such, we can provide better support for subsequent applications. Next, let us use an example to go through these four phases of our approach. Here is a code fragment extracted from a real-world project, Basin. The code allocates two containers, stack and queue, at line 1 and line 2, and then initialize the two containers by calling method initialize through call size CS1 at line 3 and CS2 at line 4. The initialized values then pass back to pointers P and Q respectively. We aim to show that our embedding can precisely preserve the dependence relations that P only refers to the stack and Q only refers to the Q object in a context-sensitive manner. Any operations through P only manipulates stack but not the Q object. The pre-embedding phase first builds an IVFG, on which each node represents the definition of a variable at a program statement, and each edge represents the def-use relation of a variable. The red and blue edges denote the interprocedural call and return value flows. The black edge is the intraprocedural value flow within a method. The call and return edges are annotated with left parentheses and right parentheses respectively, and also labeled with their corresponding numbers to distinguish these two call sites, CS1 and CS2. The IVFG is then transformed to a symbolic adjacency matrix A, with 0 and 1 denoting intraprocedural, non-reachable and reachable relations between two nodes. The interprocedural calls and returns are represented using the parenthesis symbols. In the matrix A, we formulate the value flow reachability between any two nodes using matrix multiplication. The h's power of matrix A, defined in this formula, is used to represent the h-order reachability. For example, a to the power of 2 represents value flow reachability between any two nodes with a path length of 2. More specifically, the element at the first row and the sixth column of A square represents a path of length 2 from line 1 to line 6. Similarly, A square 5 3 represents a path from L5 to L3. Likewise, for the third power of A, each element in this matrix represents a potential feasible path of line 3. For example, A313 represents a path of line 3 from L1 to L3, which is a feasible interprocedural path, while A314 signifies a path from L1 to L4, which is an infeasible path, implying that pointer Q can never refer to the stack object. The feasibility of a path is determined by context-free language defined here. By applying CFL reachability analysis, we can filter out unrealizable interprocedural passes by matching calls and returns. The resolved realizable and unrealizable symbolic passes are set to 1 and 0 respectively to produce the final binary matrix. Next, we use class index to approximate the graph's high-order approximating matrix M, which essentially is the ensemble of all feasible value flow passes. H is 3, representing the longest path length in this example. Beta is 0.8, representing the decay parameter. After resolving the symbolic matrices using CFL reachability analysis, We will calculate the class index matrix M following this equation. For example, M13 here shows the proximate value of all passes from L1 to L3. There is only one feasible path here captured by A313. We then decompose the higher-order proximity matrix M into k-dimensional embedding vectors ds and dt, so that each node will associate a source vector and a target vector. A higher proximity value, for example, produced by the inner product between i's source vector and j's target vector, implies the shorter feasible value flow passes from node I to node j on the IVFG. This table lists the reachability relations precisely preserved by our embedding. The path from L1 to L5 is the shortest, with the largest proximity value. The path from L1 to L6 and the path from L1 to L3 are also successfully preserved with lower values. The infeasible paths from L1 to L4 are also identified with a negative value, which means Q never refers to the stack object. However, without context-sensitive analysis and asymmetric transitivity preservation, the AST-based approach will collect the path from the undirected tree structure, which will produce an infeasible dependence relation between stack and queue. The fourth phase produces a final embedding vector. We use ds and dt from the previous phase to compute reachability for each node pair on the IVFG. We then collect a bag of value flow passes and their proximity values to get the final code vector. For example, we can use L1 0.5, L3 to represent the value flow path from L1 to L3. 0.5 here is the proximity value from L1 to L3. There are no feasible paths from L1 to L4, so we discard this pair. Similarly for other value flow passes. These triples are then fed into a fully connected layer to combine these three paths together to produce our value flow path vector Cn, which is formulated here. Based on these value flow path vectors and attention mechanism, we can produce a final code vector V, which preserves the interprocedural context-sensitive information of a target program. The vector V can then be utilized for tasks such as code classification and summarization. We evaluate Flow2Vec using 32 popular open source projects across a range of domains, including database, emulator, message passing tool, and so on. In these projects, we used over 17,000 well-commented methods for our experiments. 80% of them are used for training and 20% are used for testing. We compare Flow2Vec against two recent open source tools, Code2Vec and Code2Sequence, for two client applications: classification, also called method name prediction, and code summarization. This figure shows the comparison results between Flow2Vec and the existing two approaches. Flow2Vec outperforms Code2Vec in terms of F1 score, recall, and precision, with an average improvement of around 20% for the code classification task. When comparing with Code2Sequence for code summarization task, Flow2Vec improves 16% for F1, 18% for recall, and 13% for precision. This figure gives F1 scores under different code lengths. Overall, Flow2Vec outperforms Code2Sequence under all code lengths. We also conducted ablation analysis to evaluate each of the four important properties in Flow2Vec, namely interprocedural analysis, aliases, asymmetric transitivity, and context sensitivity, to further understand their contribution to the final accuracy of the two tasks. Overall, Flow2Vec with its four properties combined performs better when one of its properties is disabled, with an improvement ranging from 3.7% to 7.8% in terms of F1 score. It also demonstrates the usefulness of all the four properties when producing the final code representation. Thank you all for your time, and I'm happy to take any questions.